In this lesson, we're going to focus our attention on understanding the repercussions that our cache design has on our pipeline processor design. And so when we take a look at our pipeline, we see that in the instruction fetch and memory stages that we have now incorporated caches. And so for instruction fetch, we have a instruction cache that is utilized. And in the memory stage, we have a data cache that is utilized. And so we take this into consideration in regards to the effect of cycle times on our processor design based on our incorporation of our cache. And so we can determine that if we have a miss in the instruction fetch stage, that we will have to retrieve the appropriate instruction from memory. And so if the instruction is available within the cache, then that cuts back on our memory access time. And so otherwise it will incur at least several CPU cycles upon a miss and resulting in bubbles into our pipeline. Corresponding in the memory fetch stage, we have our data cache, and it is relevant for appropriate instructions for memory references. So if we also have a miss in the mem stage, then we will also have to introduce bubbles into our pipeline. So we want to consider that we have several algorithms that are utilized in order to provide for our cache coherence policies and mechanisms. And these are in place for reading and writing to our caches. So in the case of a read hit, we have our CPU, which is queuing to the cache to get our appropriate index and tag. And if it is available, it is sent back to the CPU. So in this case, we have data that goes straight from cache in one cycle. In the case of a read miss, we have the CPU checking to see if our pertinent data is available within the cache. If it is not available within the cache, then what will happen is we will need to go to memory. Data has to come from memory, and it'll take much longer for the data to be retrieved. The data is put on our data bus, and that is sent back to both our cache as well as to the CPU. And so in this case, if we do have a cache miss, the CPU is going to go to the memory and send the data back to the CPU and the cache. And so we can also have what is called a write-through. In a write-through, we have data is written to both the cache and to memory. And so we have two choices for writes with a write-through, and what we're going to talk about is a write-back. With the write-through, the cache says when the CPU does a write, it gets it sent to the cache and to main memory at the same time. Another way this is accomplished is also with the write-back. With the write-back, we have data written to the cache first. So if we have the data is sent to the cache in CPU, and once it is sent to the cache, it's marked as 30, but instead of immediately writing to memory, we wait until a process wants to evict the data from the cache, and then we can write it to memory at that time as well. So that can be done in the same cycles when we're writing to memory. And so you want to consider on a write-through operation as well, how it occurs. So with the write-through, we don't really have the heart at first. So this means that we need to add an additional component to allow the CPU to proceed while the memory is finishing that write cycle. So the write-through operation is going to contain an appropriate buffer. So when it does write, the value goes into the cache and then into a buffer that goes to main memory. Writes are viewed in the order that they will be written to main memory. The buffer contains the order in which the writes are received. And so if the buffer is full, then there's going to be a delay in adding additional write-throughs to the buffer that are then processed to main memory. And so if we take a look at our circuit for our Writeback Cache, we have our cache tag and our cache index that corresponds to the cache. The Writeback Cache has a 30-bit added to the cache. So when someone writes to memory, we set the 30-bit at that point. So if that value gets evicted, then it has to be written to memory as well. And so in this case, we have the cache tag as well as the tag in the cache going to our comparator and to our AND gate. And if it is hit, then that is what is sent. If we consider the case of a read miss, it can introduce appropriate stalls as well. So in this case, we have appropriate instructions, I1, I2, I3, I4, and I5. In this case, we have memory at A that is going to be stored into our R1. And then we have several add instructions that occur that are also going to make use of various registers. And so in this case, we could have R1 being used in instruction 1 as well as in instruction 5. So if we can treat a read miss in memory in a similar fashion as we did previously with registers and the busy bits. So memory can reset the busy bit for R1 when it sees that the read complete for I1 has occurred. So this provides for an alternate option instead of waiting for write back as we did before. And so let's take a look at our formulas that we have for our execution time with caches. And so we have appropriate formulas for our original time had execution time equals n times the cycle per instruction average times cycle time. Now with the introduction of caches, we have to have a effective CPI that is going to equal to the CPI average plus the memory stall average. So this requires us to make modification to how we compute the execution time. We can have appropriate formulas to relate n times the CPI effective times our cycle time, which is essentially going to be n times the CPI average plus memory stalls average times the cycle time. The memory stall averages average is going to equal misses per instruction average plus miss penalty average. The total memory stalls are going to equal n times the memory stalls average. And so I'm going to compute the effective CPI following way. If we have our average CPI equal to 1.5 and the average cash miss per instruction equal to 3% and the miss penalty is equal to 20, the CPI effective is going to be which of the following? A, 1.8, B, 2.1, C, 21.5, or D, 7.5. And so in this case, we want to do our CPI effective computation. So it is going to be 1.5 times 3% of 20 plus 3% of 20 to get the effective CPI. And so that simplifies to values of 1.5 plus 0.6, which is going to equal to 2.1 cycles per instruction. So our correct answer in this regard is going to be B. Now let's consider another example. Let's consider that we have a pipeline processor that has an average CPI of 1.8 without accounting for memory stalls. The instruction cache has a hit rate of 95%. The data cache has a hit rate of 98%. We want to assume that memory reference instructions account for 30% of all the instructions executed. 80% of those instructions are loads. 20% of the instructions are stores. And on average, we have a read miss penalty that is 20 cycles and a write miss penalty that is 5 cycles. We want to compute the effective CPI of the processor that accounts for the memory stalls. And so we can approach this scenario in the following way. We want to first calculate the cost of the available instruction misses. And so in this case, we will have our iCache miss rate times the read miss penalty. This is going to be 1 minus 0.95 times 20, which is going to equal to 1 cycle per instruction. We want to calculate the cost of data read misses. And so this is going to be the percent of memory reference instructions times the fraction that are loads times the data cache miss rate times the read miss penalty. This is going to equal to 0.3 times 0.8 times 1 minus 0.98 times 20, which will give us 0.096 cycles per instruction. Next, we want to calculate the cost of the data write misses. And in this case, we want to consider the percent of memory reference instructions times the fraction that are stores times the data cache miss rate times the read miss penalty. So this will give us the values of 0.3 times 0.2 times 1 minus 0.98 times 5. That is going to give us 0.006 cycles per instruction as the cost of our data write misses. So now let's calculate what the CPI effective would be. And this is going to be, if you recall our formula, equal to CPI effective equals the CPI average plus the cost of our iCache misses plus the cost of our Dcache misses. So this will simplify to the values that we've computed: 1.8 plus 1 plus 0.96 plus 0.006, and that is going to give us a value of 2.902 effective CPIs. And so with this solution, it's just a matter of us being able to identify and set up the problem and determine the appropriate values that we need to plug into our equation. So this provides us with a simple approach for analyzing the effects of caches on our program construction. The main thing to keep in mind is having a good understanding of the way that the problem needs to set up and making sure that you identify the appropriate information with regards to the hit rate for each cache, as well as the percent of instructions that are going to be utilized, whether they're loads or stores.